we'll go through the solutions for the 2014 ELE 2 MDD exam. Our first question has to do with microcontroller architecture and some communications and things. So we've got RISC and CISC architectures that we need to compare. So RISC stands for Reduced Instruction Set. CISC is Complex Instruction Set Computer. And the main difference is that in RISC we have a small number of highly optimized short instructions. Typically uniform length, or almost uniform length. CISC goes down the opposite route. So we have large numbers of very complex and specialized instructions. And these are typically not uniform length at all. So and the execution time varies significantly. So our MSP 430, it's a RISC. Next question. Here we're decoding some data that's been transmitted from a UART, and we're told it's 8N1 encoding, so 8 bits, no parity, and 1 stop bit. Firstly, we need to work out what the baud rate is, and then we need to work out what the message is that we're actually transmitting. So to work out what the baud rate is, we look at what our period is. So we have 1 millisecond per division. And we look at our smallest area of division, so approximately there, that's one of our smallest ones. Now we could have taken any one, for example that one there, and we know from here to here we're 1 millisecond. So we've approximately got, so that's 1 millisecond, we've approximately got here 1/5 of a millisecond, or 0.2 milliseconds. So if we say 0.2 milliseconds, we say 1 on that, it'll give us 5,000. Now 5,000, we want to go to the closest baud rate, and they're things like 1200, 2400, 4800, 9600, 9.2K. It's very close to 4800, and indeed if we zoomed right in and looked at one of these divisions in detail, we'd find it's 4800 bits per second. So that's part one. The next task that we need to do is we need to work out what the message is that we're sending, and to do that we need to first identify all the start and stop bits and then write down the bits that we're actually sending. So if we divide this way in half, we've got a start, that's bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, and that's a stop bit. So we've got another start bit, bit 0, 1, 2, 3, 4, 5, 6, 7, and a stop bit. And then we have a start bit, 0, 1, 2, 3, 4, 5, 6, 7, and a stop bit again, and a start bit, 0, 1, 2, 3, 4, 5, 6, 7, and our final stop bit. So now we can write those out in order. So starting from here, we go low, high, high, low, 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 high, low. So starting at we're doing least significant bit down here. So 0, 1, 1, 0, 0, 0, 1, 0. That's our first one. Our next one, we're starting at this point here. So 0, 1, 0, 0, 1, 0, 1, 0. Our next one, we start with 4 ones, 1, 1, 1, 1. So that's this area here. 0, 0, 1, 0. And our final one, 1, 1, 1, 0, 0, 0, 1, 0. Now we can convert those all to a hexadecimal form, and once we've got them in the hexadecimal form, it'll be very easy to convert them and work out what their ASCII representation is. So we've got 0x4 6, 0x5 2, 0x4 F, and 0x4 7. We can then bring over an ASCII table and look at what those things are in the ASCII table. So 46 is an F, 52 is an R, 4F is an O, and 47 is a G. To me, that reads as frog. Okay, next we've got what are ADCs and DACs? Describe the purpose and implementation of one type of DAC and one type of ADC. Now we need to remember to answer both parts of the question. If we only answered what ADCs were, or only answered what DACs were, we'd only get half the marks. We need to also describe what they are and describe the implementation. So let's start with ADCs. ADC, they convert a continuous analog voltage to a quantized digital representation. For DACs, convert digital value into an analog like continuous voltage. Now, of course, it won't be completely continuous. It will be in small steps, but it will, if we make those steps small enough, it'll look almost continuous. So we've said what they do. We're just essentially the purpose for our ADC. We allow our microcontroller to read analog voltages. For our DAC, we allow microcontroller to create or generate digital analog voltages. And we need to describe the implementation of one or the other. Now, we could use any implementation we wanted at this point in time. So for a DAC, I'll describe PWM. For our ADC, we'll describe our ramp compare or integrating. Now, you don't need to describe those particular ones. You could have used a flash ADC or a successive approximation or anything like that. So, pulse width modulation. We generate a constant period, but varying duty cycle. Square wave. And our analog voltage is proportional to the duty cycle. And we put a low pass filter on to make it look more analog like. For our integrating, essentially we have a comparator and we have an input voltage and a voltage that we ramp up. So input voltage compared to ramping voltage. And when the input voltage equals the ramping voltage, we've done our conversion. Equal to ramping voltage. Conversion's complete. Okay, our next question is on watchdog timers. So our watchdog timer is a timer which, when it times out, resets the CPU. we use it for protection. Essentially, we don't want to get into a state where we can lock up our CPU. So essentially, allows CPU to automatically reset. And we're talking about how does it operate. Why is it important first? Often we're designing microcontrollers that will operate in environments that are inaccessible and we can't get to them to reset them. So they might be in space, they might be thousands of kilometers away from the nearest person. So we want microcontroller to keep running even if we aren't there to reset. And how does it operate? We periodically pat the watchdog. Basically we set the timer, watchdog timer value is reset. And if we can't pat the watchdog, if we don't patch the watchdog, it will time out and reset the CPU. Okay, our last question for part 1. We need to specify the addressing modes, so for source and destination, and then need to calculate the physical address for each of these. So addressing mode, symbolic, indirect, auto inc, immediate, register, indexed, absolute, indirect, and register. Okay, for working out the physical addresses, we go through. For symbolic, the physical address is what's specified, so it's A850. For indirect auto increment, we go to the register, which is R6 up here, and we say it's 0x0198. Now after that instruction, register 6 would increment, but not before it. Next, for immediate, we don't have an addressing mode for immediate. There's no physical address. For a register, it's just the register name, so we'll fill in both of those ones. For indexed, we look at what that register points to, so 198 in hex, and we add the offset to it. We add 2 to it, so it's 0x019A. Another absolute one, so AA40, and we go to register 5, it's indirect, and we put our value in there. Okay, on to question 2 now. Here we're designing a microcontroller system and we're told all the things that need to be connected to it. First thing we need to do is draw our circuit. So, microcontroller system should have a microcontroller that sits in the middle of it. And we need to supply power and a decoupling capacitor. So we've got a 3-volt power source there. We've got a ground. And we've got a 100 nanofarad decoupling capacitor that decouples it. So our first one's done. We've got 4 LEDs connected to it. And we're told what the current is and what the voltage is for each of those LEDs. And we need to do some calculations later on. So let's connect up our LEDs first. Make sure you draw the arrow on them, otherwise they're just diodes, and diodes don't light up unless something's gone catastrophically wrong. So we've got 4 LEDs. We'll label the resistors R1, R2, R3 and R4. We need to do a calculation for those, so we'll say R1 is equal to R2, which is equal to R3, which is equal to R4, so they're all the same value. R1 is equal to, we're working off 3 volts up here, so 3 volts minus, we've got forward voltage across the LEDs of 1.8 volts, 1.8 volts divided by 10 milliamps. So when we do that calculation, it should give us 120 ohms for each of those resistors. So we've got our LEDs and resistors in place. We've got 2 push buttons, and one push button needs to use the internal pull-up resistor and one needs to use the external pull-up resistor. So we'll do one of them over here. So remember, we have external pull-up resistor of 10k and a little push button, and this one will use the internal pull-up resistor, and we just don't connect an external one. Now, I've talked about using justification. So why do we use a 10 kilo ohm resistor there? We say 10k resistor is large enough to not waste too much current when button is pressed, small enough to stop pin from floating. Now we can very easily work out how much current would be going through there if the button was pressed. So I equals V on R. We've got 3 volts up here. 3 divided by 10k. which is 0.3 milliamps. In other words, not very much. So we've taken care of our switches. Our final one is a potentiometer that we're going to have. So we'll have our 3 volt supply there. We'll connect our potentiometer here, and that can directly go into one of our analog inputs. Now what we need to do is work out where those things are actually connected. So if we look over here, we're told we need to connect our analog input, our potentiometer, up to one of the analog pins. So we need to look for one that's got A0 or A1 or A2 or A3 and so on. So for sake of ease, let's connect it up to A0, this pin here. So we'll say it's on P1.0, which has the analog input 0. So we'll say P1.0. Now we have pretty well complete choice with the other ones. I'm just going to count up P1.1, P1.2, P1.3, P1.4, P1.5 and P1.6. Okay, next question. We're asked to write an embedded C function that sets up the direction of the pins and the pull-up resistor from the previous circuit. So we'll write our function. We'll call it something like init.io for initialize input output. So we don't supply any parameters to it. So we know P1.0, P1.5 and P1.1.6 are all inputs. All the rest of them are outputs. Now we know an input we need to put a 0 in the register, and output we need to put a 1 in the register. So let's work that out. Firstly, we're saying P1 dir is equal to inputs are 0, outputs are 1. So we're looking at 7's an output because it's not connected to anything, and if it's not connected it should be an output. 6 is an input, 5 is an input, 4 is an output, 3, 2, 1, 0 in binary. So if we convert that into hex, because in C we can't deal directly with binary, we've got 0x9e. So 0x9e. So we set all directions of the pins. We need to do the pull-up resistor as well. Now we connected the pull-up resistor to P1.6. So P1 REN, resistor enable, is equal to, we can just say directly, bit 6. Okay, next question was the purpose of the capacitor in the circuit. The capacitor is a decoupling capacitor. And it basically ensures that the microcontroller itself is decoupled from the supply line. So any switching noise that the microcontroller generates won't be coupled onto the supply line, and any switching noise that any other components in the circuit might be generating, like when we're turning LEDs and things on and off and currents are changing, won't be coupled into the microcontroller. So it ensures we get a nice stable voltage into the microcontroller. So we'll just summarize that. and hopefully we'll have a nice stable voltage on our voltage supply line. Because that's important for digital devices. Okay, now we've got our pull-up resistor that we're talking about. Why do we use a pull-up resistor? Well, think about our circuit for a moment. If we didn't have a pull-up resistor and we just have the switch, if the switch is not pressed, we have essentially this high impedance input connected to nothing, which means it's floating. If we put up our pull-up resistor there, it stops it from floating. So resistor pulls up pin and stops floating when button isn't pressed. If it wasn't connected, the voltage could be high, voltage could be low, we don't know. Could be affected by just noise in the circuit or radio waves and things like that. It essentially acts a bit like an antenna. So it ensures all inputs are always applied with a known voltage. We've got a 10-bit ADC. What would be the output of the ADC if the potentiometer was adjusted to have an analog voltage of 1.95 volts, assuming the full scale voltage is 3 volts? This question is really in two parts. First, we need to calculate our step size. Once we've calculated our step size, we can use that to calculate what the analog voltage or the digitized voltage would be. So firstly, our step size, we have 3 volts divided by 2 to the 10 minus 1, which gives us 2.93 millivolts per step. Now we're saying we're having 1.95 volts. So we say 1.95 divided by 2.93 millivolts. When we perform that calculation, we find it's equal to 665. And so this is the value that our ADC will return to our microcontroller. Basically, you'll note that I've said include a timing diagram and a flow diagram to describe how we'd implement something like this. And basically the way it works is we have an RC circuit. Now, an RC circuit has a characteristic charge-discharge time. And typically what we're having is a very small capacitor and a very large resistor. So, and when we touch it, our body introduces additional capacitance. So when touched, so we change the capacitance, and hence tau, or our time constant, changes. So essentially what we're looking at graph-wise in our timing diagram might look something like this. If we're not touching it, we might have a charge, discharge, or a charge curve that looks like that. If we are touching it, tau gets longer, and so we might have something that looks like this. Now, if we pick a certain point to do our measurement, so there's our 3 volts. If we pick a point over here, for example, and say, okay, at that point there, we want to check our measurement. So we send the pin high, we let it charge up and see where it gets to. Now, in the case that we're not touching it, you'll get to that point a lot faster. In the case that we are touching it, it'll get to, or when we wait that time interval, the voltage won't be nearly as high, and so we can actually measure that. So our code might look a bit something like this in our flow diagram. Set pin high. Then we want to have a short delay. And then we want to say is so we want to say, is it charged? If yes, then we're not pressed. Because we've followed this route and the capacitor's charged up enough. If no, we're pressed, because it's taking us longer to charge up because our time constant's long. Okay, for this question, we've got an assembly language question, and we need to create a subroutine. So let's create our subroutine. We need a label. We'll call it setup ADC, and then at the end of the subroutine we need to return, so a ret. We want to do the following, and we need to refer heavily to what's in the appendix to do these sorts of things. So firstly, we're going to start pin 1.5 to read from the ADC. We're going to use a polled mode, so not interrupt. We're going to use VCC and VSS as our references, SM clock as the ADC clock, and no clock divisions. So basically what we need to do is we need to heavily refer to the appendix and work out what the relevant areas are. So firstly, we're saying we're going to be using P1.5, and we actually need to enable that in 2 different places. First place we need to enable it is in the ADC10 analog enable register. So we're using pin 5, this one here. We need to set that one to a 1 to enable it. If we have a 0 there, analog input's disabled. If we have a 1, analog input is enabled. So we set that one to a 1. The other thing that we need to do is choose the right input multiplexer for our ADC, and that is going to be based on our what bit that we're using. So we're using pin 5, P1.5. P1.5 is connected to analog A5, analog input 5, and we can see that if we look at the ADC pinout. So P1.5 has analog input 5. So when we're setting up our ADC, we need to be using analog input 5 in these bits here. So let's set some of those things up. Firstly, we need to put the right value in the ADC10 analog enable register. So we're saying move, it's an 8-bit register, so we need a .b, and we need bit 5, so we say 7 6 5 4 3 2 1 0 into ADC10 AE0. So we've enabled the analog input there. What we then need to do is deal with our other registers. And one thing with the other registers is most of the values in them, these ones up the top here, are greyed out. And when we're greyed out, we can see that it says these can only be modified when ENC is equal to 0. And it's the same with our ADC10 CTL1 register. Most of the settings there can only be modified when ENC is equal to 0. So we need to set ENC equal to 0. So that one there. Easiest way to do that is to clear this whole register. So we'll set ADC10 CTL0 to 0. So if we say clear ADC10 CTL0, and we'll put some comments there. Set ENC to equal 0. Okay. Now let's go through our other registers and work out what needs to be done. So firstly, for the ADC10 CTL1 register, we need to set the input channel as A5. So those top bits should be 0, 1, 0, 1 to correspond to A5, 0, 1, 0, 1. We're not doing sample and hold select, we don't need to change that. Those things are the same. We set a clock divider of 0, or a clock divider of 1, so we're not dividing the clock down. So we choose this one here. We've also specified that we want to use the SM clock, so we need to set bits 3 and 4 to 1, 1. And the rest of them are all conversion, single channel conversion, and it's not going to be busy, so we're not actually using it at this point in time. So we need to move a value into that register. So move.b, and we want to start off with setting the top 4 bits. So 0, 1, 0, 1, that specifies it's A5, and then 0, 0, we're not using those. 0, 0, the clock divides the next 3 bits, 0, 0, 0, we're not dividing our clock down at all. Our clock select is the next 2, and we're choosing the SM clock, so 1, 1, and then 0, 0, 0. So we've set it up, and that's the ADC10 CTL1 register. So we'll just put some comments there. A5 selected. SM clock selected. And we can even cross some of these things off. So now we've set up P1.5, that's all done. We've chosen the SM clock, we've chosen no clock divisions, so we're halfway there. Next thing we need to do is look at the CTL0 register. I've specified a few things in here. One is our references, so I've said we're using VCC and VSS as our references. So those top 3 bits there need to be 0, 0, 0. We don't need to worry about a sample and hold time. These things we just leave in their standard 0 state. Those things are all standard. We need to turn the ADC on. So bit 4 we need to set to a 1. and we're not using interrupts, so we leave all the interrupts off, and we'd use this one to start the conversion. We'll be doing that later on, but we don't need to do that in the setup. So we need to turn the ADC on. Once the ADC is on, we can then do our enable conversion. So let's set up that register. So we'll say move.b, we've got the reference we set up, so VCC and VSS. These ones we're not using. Not using that one. We're not using our reference output. Don't need to do burst reference. Not using the 2.5 volt reference. We need to turn the ADC on, and we set all our remaining ones to 0. So we selected our reference and ADC on. Then we want to set the ENC bit to 1. So we say bit set, and these ones should actually be not.b because we're moving a full word in there, not just a byte. And we're interested in bit 1, so 15, 14, 13, 12. So bit 1, ADC 10 CTL0, and I'll put a comment there, ENC is now set to 1, and our ADC is all set up and ready to go. And of course we have our return statement down the bottom there. Okay, now we want another subroutine, and what this subroutine is going to do is it's going to start an ADC conversion, poll the ADC and check that it's still converting, and then return the result. And we'll return the result in, well, we'll choose a register that we can return the result in. Now, a few things to note. In the ADC 10 CTL0 register, the bottom bit is the start conversion bit. So if you look at what it says at that bottom bit, if we set it to 0, we're not doing a conversion. If we set it to 1, it's going to start a conversion. So that's how we actually start the conversion. We just set that bit to a 1. If we want to know if we're still converting, our bottom bit in the ADC 10 CTL1 register is the busy bit, ADC 10 busy. If we look at what it says, if it's 0, we're not performing conversion. If it's 1, we are. So we need to wait until we're not performing a conversion anymore. So let's write our code. We'll call it read ADC. That can be our label to start our subroutine. Remember, we need to write these things as a subroutine. So we need to start the conversion. So we say bit set. We need to set the bottom bit, so we'll just put in 1 there, to ADC 10 CTL0. So start conversion is set to 1. So we start the conversion. We then need to check that that conversion is still going before we do anything else. So we'll say something like bit, and we're going to check bit 1, but we're going to check it in the ADC 10 CTL1 register. And we're basically saying is busy bit still equal to 1. we'll create a label here that we can jump to, and we need to say jump not 0, so if it's still equal to 1, to busy. So while the ADC is busy, while it's reading, the bottom bit in ADC 10 CTL1 is equal to 1, and we keep jumping around here and doing this loop again and again and again. When it's finished, what we can then do is we know our results in the ADC 10 mem register. So we move ADC 10 mem to, I haven't specified what register we're going to put it in, so let's put it in R7. And we'll do our return to end the subroutine. Okay, here's some quick and easy questions. Firstly, we're going to set these two as inputs and all the other ones as outputs. Easiest way to do this is we say move.b and we specify what we're doing. So an input we need to set it to a 0, an output we need to set it to a 1. So 7, 6, 5, 4, 3, 2, 1, 0. P1 dir. We need to flip some bits, so flip bits 5, 2 and 1 in register 6. So to flip bits we XOR them with 1, so we're XORing bits 5, 2 and 1 in register 6. And we're going to add 21 to the value of the memory location pointed to by R6. So we need to say add. We're adding the value 21, so we need to use add immediate. And pointed to by R6, we use indirect addressing R6. These ones we need to step through our code and see what the end result's going to be. So obviously if we're moving this into R7, we'll know what's going to be in R7. We can write that out in binary to make it a bit more obvious for us, particularly with this inversion one. Okay, we invert R7. If we invert R7, all our bits are flipped. Now the result of that, so we've got 0, we've got F, 5 and 5. Once again, we'll write out the value that's in there. 10, 10, 10, 10, 0, 0, 0, 0, 0, 0, 0, 0, and we're XORing it with 0x, 0f, 0f. So these bits will be flipped and these bits will be flipped. So our end result will be, they stay the same. These ones we flip. These ones stay the same. And these ones we flip. So that will be A50F. We're putting the value 25 into R7 and we're rotating left by 1 position. Remember when we rotate left we shift a 0 in the bottom. We can also think about it very easily as if we rotate left we multiply by 2. So R7 will now equal 50, which is 25 multiplied by 2. Okay, in this subroutine we're performing integer division between two values. And because we don't have explicit, we're not a CISC architecture, we've got an explicit multiply and divide instruction, we need to do this by successively subtracting things and do it in a loop form. So let's create our subroutine. We'll call it div Within the subroutine, one thing that we want to do is we want to reset our destination and make sure that's going to equal 0. So we'll clear that, clear R10, that all equals 0. And then we need somewhere to loop back to, because we'll be looping around and doing various things. So loop, create our label there. And think about division for a moment. Basically, you're looking at how many times one number can fit inside another number. And for integer division, you're looking at how many times it can fit inside the other number as a whole number. So what we need to do is some successive subtraction. So we sub R9 from R8. So we're looking at how many times R9, which is a small one, can fit in R8, which is the larger one. We're going to compare R8 with 0. So we want to see, okay, are we out of room in R8? And then we're going to say jump less, so JL, to, we'll call it exit. That's essentially where we're going to finish our function. So we'll write that down here. Exits, and in here we'll say return. So what this will do, if R8 is less than 0, it's going to allow us to exit our function. But if R8 is greater than 0, so it's 0 or anything else, it will allow us to keep on going. Now, each time it's not equal to less than 0, we need to increment R10, because we've just discovered another time that R9 can fit into R8. And then we say jump to loop. Now think about what we're doing. So we subtract R9 from R8, we compare it against 0 and see if it's less than 0, and if it's not, we increment R10 and we go back to the start again and do it again. If it is less than 0, so it might be FFFF or FFFE or something like that, we go to exit and return our return value, which is okay. For the previous question, describe how your subroutine might be more efficient if the value in R9 was guaranteed to be a factor of 2. Now, I haven't asked you to write it in detail, so basically what we need to recognize is division by a factor of 2 is basically rotates. So if we rotate right, we divide by 2. If we rotate right twice, we divide by 2 twice. So rather than having a series of loops and subtracting, we can have a small number of rotates. Okay, this one here, we've got an embedded C function. So first thing we'll write is a function, we'll call it flash LEDs. So void flash LED ASCII. And it takes a ASCII byte, so we'll say char, and we'll call it ASCII input. Okay. So it takes an ASCII input. Now the numbers in ASCII to represent a number from hex 30, that represents 0, through the hex 39, which represents 9. So we can represent 0 to 9 with 0x30 and to 0x39. And just for proof of that, we can turn to our ASCII table and we look at our hex values. 0x30 equals 0, 0x39, it represents the number 9. So this function should flash an LED on P1.5 number of times specified by the input number. So if we give the value 34, this corresponds to number 4, and we should flash the LED on and off 4 times. And we've got a delay function that we can call. So first thing we need to do is work out how many times we're going to flash it. So we can declare an integer, int flash cycles is equal to we say ASCII input minus 0x30. So we're subtracting 0x30 from that, and that will give us the remainder. So if we subtract 30 in hex from 34, it'll give us 4, which is the number of times we want to flash on and off. So we've done that. Now we can use a basic for loop or a while loop or something like that. So we'll just declare a for loop. For I is equal to 0, I is less than flash cycles. I plus plus. And we want to turn the LED on, delay, turn the LED off, and delay. So we say P1 out. So we set bit 5 to high to turn it off. Delay. Then we set bit 5 to low to turn it on. And we delay. Okay, our next question is on debouncing. So firstly, use timing diagrams to show why a button may need to be debounced. We're talking about when it might be used, when it might not need to be used, and then write some C code to show how we can do some debouncing. So first, a timing diagram. When we press a button, we invariably get something like this. Goes up and down for a few cycles, and we can label this. This is when the button was pressed. And what we've got here is our bouncing. Okay, when is it required? When is it not required? We need to say something like it's required when number of presses is important. We can also say something like if only state of in this case, our debouncing isn't required. Okay, now we need to write some code. So we've got a button that we're going to debounce on P1.0. We're going to toggle an LED on P2.4 each time it's pressed. So we need to write something like this. Let's do a quick flow diagram. Is button pressed? No. We'll reset a counter. We'll reset a counter to maybe 20. That will delay for a short period of time. If it is pressed, we'll have a short delay, so maybe a 1 millisecond delay. We'll decrement our counter. So we decremented our counter. Then we need to check, is the counter equal to 0? If it is equal to 0, we're debounced. If it's not equal to 0, well, we go back up to here and we keep looping through until it does equal to 0. So if it's equal to 0, we're debounced. We need to toggle the LED. So toggle LED. Once we've toggled the LED, we need to actually wait for the button to be not pressed anymore. Otherwise, we just keep on flashing the LED on and off. So we say, is button pressed? If we say yes, we want to just wait in there for a while. If we say no, well, then we can go back to the start again. And this one will need to loop back there as well. Okay, let's put that in the form of some code. So we're going to be looping forever, so we'll say while 1. First thing, is the button pressed? So we say if 0 is equal to P1 in ANDed with bit 0. So is the button pressed? If yes, we delay. So we'll call our delay. Then we count down, so CNT minus minus. Another if statement. If CNT is equal to 0, then our thing's debounced. So at that point there, we can flip the bit. So we're flipping P2.4, P2 out, XOR with bit 4. And then we need to wait while the button's still pressed. So we say while 0 is equal to P1 in and bit 0. Wait while the button's still pressed. Okay, we've done all of this side of it. Now we just need to do this side of it. And essentially all we need to say is else we set our counter to 20. There we go. We've got our code for toggling the LED each time the button's been pressed. Okay, here's another one that we need to refer to our data sheets for. What we want to do is we need to set up the timer, and we want to generate an interrupt every 5 milliseconds. We'll be using timer 1, and we're going to use up mode for the timer and SM clock for the clock, and we've got a 1 megahertz clock. So firstly, if we have a 1 megahertz clock, that means we have each clock count is 1 microsecond. Okay, 1 divided on 1 megahertz gives us 1 microsecond. This means to get 5 milliseconds, we need 5,000 counts of our timer to give our 5 milliseconds. Okay, let's look at our timer for a moment, our timer registers. Okay, our overall control register for the timer. We need to choose our clock as SM clock. So we need to specify these bits here, bits 8 and 9 in our timer, bits 8 and 9 are going to be SM clock. Now, the input divider, if we wanted to slow our clock down even further, we could use our input divider there. We're going to be using up mode. It's asked us to do that in the question. Timer should use up mode. And these ones here, we want to generate an interrupt each time the timer times out. Now, it times out when up mode counts up to the value in TACCR0. So if we put 5000 in TACCR0, the timer will count up for 5000 counts, or 5 milliseconds, then it will time out and generate an interrupt. And that interrupt is down here. So all we need to do is basically sub this timer. So TACTL is equal to the top few bits we're not going to use. We're going to use bits 8 and 9. So to set the clock as the SM clock. So bit 9 gives us the SM clock. We then OR that with, we're going to be using up mode, so we set bit 4 to 1 to use up mode. And we also want to say interrupt and enabled, so that's bit 1. Okay, this will set the clock to count, or set the timer to count. It'll generate interrupts anytime that happens to equal, or the timer count value equals 5000. One thing that we need to do before this is actually set up the 5000 part. So we've been told here in the question, in up mode the timer will count up to TACCR0. So for TACCR0, we say TA0CCR0 is equal to 5000. And there we're done. Timer's set up, it will count up to 5000, reset itself to 0 and generate an interrupt. Now if we were toggling a pin, for example, we'd need to do it slightly differently. We wouldn't use interrupts for starters, and we certainly wouldn't use the interrupts on the timer control register. Where we would use them though, or where we would set things up, is in the timer capture compare control register for the particular bit that we were wanting to flip. So in this register we can set our output mode, and that's the output mode that will toggle specific pins. So we say output mode, it might be on toggle or something like that, and we use that to toggle a specific pin connected to a capture compare register, like TA0CCR0 or TA0CCR1. One final thing on this, we'll need to make sure our interrupts are turned on globally, so we use the function eint, and that will turn on interrupts for our device. Okay, a few quick questions here. Embed C to invert bits 0 and 2 in the variable D. So D XOR equals, so we use XOR to invert bits, bit 0 or bit 2. Clear bits 5 and 2 in the variable B. So B and equals, we use and to clear bits, bit 5, bit 2. Set bits 2 and 4 in the variable A. So we use OR equals to set bits, bit 5, bit 2 or bit 4. And finally, clear bit 7 and set bit 0 in the variable C. Now we could do this as 2 lines of code, or we could do it as one compound line of code. So we basically say C is equal to, we'll say C ANDed with, not bit 7. So that will clear bit 7, and we're ORing that with bit 0 to set that bit.